So here's the recording. I'm gonna go ahead and share again. Sorry, I have to unshare and then reshare in order to record. All right, I'm going to go ahead and minimize this. All right, so today we're talking about relational parameters. And so what I've done in advance is I just created a quick sort of scenario, design scenario in Rhino here. There's just sort of two serpentine walls. They don't even have thickness. They're just really just the sort of paths, right? And again, they're just sort of extruded as surfaces, but they sort of climb. Sorry, they sort of are serpentine in nature and plan. You can see they sort of wind around their splines. And then in elevation, they sort of start low and then they sort of climb their way upwards, and they climb at different rates. So you'll see some, the wall sort of, let's say this right wall sort of climbs a little higher than the left wall. And then by the end, the left wall actually climbs higher than the right wall. And so, if we were going to look at this scenario and then ask ourselves, how do we span in between these two load-bearing walls with a set of trusses in order to create a roof, right? Or to create, let's say, a glass roof. This was some sort of greenhouse. All right, so I'm going to show you where we're going to go with this. So go ahead and open up Grasshopper. Okay, it's right down here. And I'll show you in advance what we're going to do as a sort of demonstration, what I'm going to do in front of you. What I recommend is just sort of watching. You don't necessarily have to follow along. This will be mostly a review of the things you've already done with those first 11, 12, maybe 14 videos, but maybe those first 11 videos or so that you watched last week. And so, you can just sort of watch, and I might ask some questions and just, make sure that we're jogging important things in your memory, right? But it's mostly a review, but we'll take things a few steps further here. I'm just hearing myself. Okay, great. I think someone muted themselves. All right, great. All right, so first up, what we'll do is we'll instantiate a set of trusses along spanning between these two walls, right? And so if I just go, this is like a cooking show. I'll show you the prepared thing that I take out of the oven first, and then I'll show you the step-by-step, and we'll make it ourselves. All right, so here's a set of three-dimensional bow trusses, right, that sort of span between these two walls, right? And so, it's not too much different here than some of the things you've done in the past. Right, we'll just look at Grasshopper a little larger here and more close up. Where did my cursor go? Oh no, where'd it go? There it is. All right, great. All right, sorry about that. And so what I've done is I've taken the sort of top edge of one wall and the top edge of another wall as curves and brought them into Grasshopper. Each of those curves I divide a certain number of times, right? Then I connect each of those divisions up, a start point and end point with a line. Okay. So let me just quickly, I'll just turn off the previews and we'll build this up step by step just to sort of go through the recipe here. Okay, so you can see I have these two green curves here. I'll just maximize my perspective view. Let me just make sure this all fits on the screen so we can sort of look at the preview in Rhino, the geometry itself. We can look at, I don't know what's going on here with my machine. Here we go. All right. Okay, so you can see these serpentine walls. I've highlighted these green curves I brought in from Rhino into Grasshopper, right? So these top curves were curves I drew in Rhino in order to create the sort of top edge of these two walls that I'm spanning in between. I bring them in, I can divide them, in this case, a variable amount, right? So right now it's set to 35, right? Just turn those on. At each division, I get a point, right? So I'm basically populating these two curves with a set of points, right? That are sort of spaced depending on how many times I divide these curves up. So, if I need more trusses, more dense, less space between them, I can divide these more times, right? So I can, I could go crazy with that and divide them 500 times, or something more along the lines of, let's say, I'll just double click and set this to 75 for time being. Right, so now I have basically a set of points along this top edge, a set of points along this top edge. One of the things I can do is I can connect each of these points up as a start point and end point with a line. So that's what I'm doing. I'm going to turn those on. Right, so I plug in this set of points, right, that I've generated for the start point, or a set of start points, and this list for a set of endpoints. So if I have 76 start points and 76 endpoints, I get 76 lines out. Right? Okay, so now we sort of have a rig, right, or the starting scaffolding for the trusses that we're going to build, right? And so this is literally a line spanning across the sort of minimum span that each truss has to sort of reconcile here. All right, I'm going to take each of these lines, right, and I'm going to evaluate them at t parameter. All right, right now they're set at 0.25. I can set that to 0.5. Right? In other words, I can draw a point somewhere along each of these curves. Right? I can move that because the t parameter is a variable. This number slider, I'm just going to set it to 0.5 and try to find the midpoint of each of these curves for the moment. Of course, we can change that at any time. Right? We change it here. All the changes propagate from left to right as the information flows across the graph, right? And so the output of one node becomes the input for the next node. Right? All right, so we get these points, and what I'm going to do, similar to how you guys did your bow trusses, is I'm going to use a z vector, and I'm going to give a number for a length, and I'm going to draw a line, right? Using these points as my starting points, the z direction as my direction, and then this number slider to determine the sort of length of this line, right? All right, you can see these lines, I can sort of grow them. I can change the starting point, right, by sort of deciding where I'm evaluating each of these spanning lines, right? So you can see I'm starting to get a sort of robust graph here, and that I can begin to change things around by adjusting the variables. Right? Now, in this case, instead of just projecting upwards, I'm also going to project downwards. So I've also done the exact same thing, right? But now what I've done is I've used the z-axis for my direction, but for the length, right? I've plugged in this number slider for my length for this widget, right? But I've also plugged it in for this other widget, but you'll see that there's an asterisk here. What I've done is I've just written a handwritten expression in here that says, take whatever I plug in for the length and multiply it by -1 so that I get the negative value instead of the positive value. Right? You don't necessarily have to remember that small detail, but that's, I mean, conceptually, I hope this makes sense. What I'm doing is I'm drawing a line in the z-axis that's 3.237 units, and I'm also drawing a line that starts from the exact same point going in that z-axis direction, but -3.237 units. So it's going in the other direction, right, along that z vector. Right? I find those start and end points. Right? And I'm going to take those, and I'm going to take my endpoints that I used way over here. Right? I'm going to plug them in to make my my sort of arc, or sort of bow, arc-shaped bows across both the top and the bottom. Okay. So at this point, I'm just going to turn some things on and off here so you can see things a little more clearly. But I'm going to turn these on. You can see that I have my top arches, I have my bottom arches. Okay, I'm going to turn off some of these other, the construction geometry that we just laid down. I'll turn that off just so we can sort of see what we have here. Right. They're still being generated. They're still here. They're just gray, right? It means they're not being displayed, and sort of getting rid of some of that construction geometry as we move past it, right? It's still being generated, still being used, still being calculated. But we don't necessarily need to see it all on the screen at the exact same time. So getting rid of some of the visual clutter at this point. But as you can still see, I can adjust these as I need to, right? Both in terms of how the size of the trusses and their internal geometry. I'm doing something funky that we didn't talk about here, and that is I'm grafting some of these lists into data trees. And it's fine if you don't know what data trees mean. I wouldn't expect any of you, or at least most of you, to know what that means, especially if you've had no experience with Grasshopper and scripting before, right? But what that basically means is that I have a number of sort of items in these lists, and I need to organize them in a different way because I'm starting to do not just one truss, but lots and lots of trusses. And so I start to get lots of different sets of points and curves and things like that. And so it's a different way of storing these things in order to keep them organized later on. That comes in really handy. And you'll see, right, that there's a shift here in the way these sort of rubber bands between, sort of connecting one node up to the next. They were solid lines, solid rubber bands, until I get to here. And then suddenly I get a data tree and the rubber bands are dashed, right? And so we'll continue to talk about that. And we'll talk about that more explicitly and talk about what that means in project 2. I just wanted to sort of, again, if you're noticing this sort of these visual shifts in the graph itself, that's why, right? So I don't expect you to know all of these details here, but I just want to sort of show you, how we could take the stuff that you did in those first 14 videos further, right? And sort of deploy, let's say, in this case, we're deploying a set of trusses, but in the economy of scale, right? So now, this graph becomes super important because we're generating, maybe hundreds of trusses and they're all different, right? Because each of these spans are different, right? And so this is where parametric design really comes in handy in order to generate this sort of repetition and difference in managing it and making it both feasible when it comes to the sort of designing construction management and also budget, right? So, and we'll talk more about production constraints and fabrication in project 2 as well when it comes to this sort of idea of serial differentiation, right? We have a sort of a recipe to create a truss, right? But each one is slightly different to the next, right? And they sort of serially differ as we move across, in this case, this volume that we've created in between these two sort of serpentine walls, right? So, all right. Nevertheless, we have the top chord and the bottom chord for each of our trusses, right? So now we're going to divide those up. We're going to divide each of those up the same number of times. I can, again, change that number and that density, right? But what we're going to do is we're going to use those. We're just going to play connect the dots with lines, right? So we're going to connect each one up one to one. You can see here, hopefully. Let me just go actually over here. I'll go to the end. You can see these sort of larger trusses, hopefully. Oh, sorry, I'm not being very successful. I'll change the sort of center of my rotation here, and when I tumble and dolly around my viewpoint, right? So you can see a top chord and a bottom chord, right? And then I'm starting to connect them up. All right, there they are. Yay. All right, now I'm also going to take each of these lists and I'm going to shift them by one, right? And that way I can start to make some diagonal webbing, right, when I start to connect these things up. All right. And so now not only have I made those sort of vertical webbing, but I can make this sort of diagonal bracing and webbing in between, right, for each of these sort of modules inside each of these trusses, okay? All right, you can see that it gets quite dense. And each of the lengths of these, each of these struts are going to be completely different from the next within each truss, and then from each truss to the next truss, right? So that's the important thing here is starting to manage this. It would take an awfully long time to manually model and draw each of these, right? Trying to snap and trying to find the same distance along each of these walls, and it just takes an incredible amount of time. And that's, again, this is where parametric design really helps, right? As you start to take something silly like a large expanse here, right, and then actually break it down into the sort of architectural components that you need, right, and they have to be built and made and then assembled on site. Managing all of that, right, becomes important, and that's what these tools are for, right? And later on when we talk about Revit and BIM, right, becomes even more underscored, right? So that's what we talk about, this sort of idea that the digital model is really the sort of database with all of the information you need in order to visualize things, certainly, but then to realize them on down the stream as you hand off this information to all the people that have to engineer things, that have to optimize things, that have to fabricate things, that have to build things and assemble things, etc. Right? So, you know, I'll just quickly clear out that red chicken scratch there. All right, so there's a set of trusses at uniform depth. Now, what's interesting about this is that, right, this length here for these lines that we drew, right, the sort of height, that sort of structural depth of the trusses, right, we've made a really big assumption that I wouldn't necessarily make if I was doing this for real, and that is that each of these are going to be the exact same depth. So if I'm spanning 1 foot, right, these things are going to be really deep, even if in the same depth as if I'm spanning 20 feet or 40 feet, right? And structurally, that's not the way things work, right? So the longer you have to span, the deeper a beam or a truss really has to be, right? In order, I think you sort of understand that maybe implicitly, right? But suffice to say that if I'm building a bridge and it's a really long bridge, right? And it's, you know, it's spanning across a very wide, let's say, river, like the Mississippi River, right? The structure for it's going to have to be much deeper than if I'm spanning, let's say, a drainage ditch, right? That's only about a foot wide. and so, you know, I think that's one of the things that we wanted to talk about today was this sort of building in some of these geometric relationships, so that we can begin to make these things smarter, more intelligent, optimized for performance, right? In this case, structural performance. Okay, so let's just talk about this for a moment, right? What I'm going to do in this next graph, again, I'll stop and build these from scratch, but I just wanted to sort of show you what we're going to do here, is I'm going to, instead of using just a standard number here, right, like one constant, like 4.089 or something, is what we'll do is we'll measure the lines that we draw across the span and get their distance. Each of these distances will be different, right? I mean, I think we understand that if we look in top view and we look at these green lines, right, we'll understand that each of these lengths will be different, right? Because the distance that they're spanning are different. And then we'll use those numbers and we'll apply a formula to them in order to get each of these depths, right? And so as we change the serpentine wall, right, or a structural engineer gives us more structural information, right, then we can basically customize each truss so that it's just the depth that it needs to be based off of the span, right? Okay. So in this next graph, let's just take a look at the difference here. Relational depth. I've done just that, right? And so what I've changed, I've made a change right here to these widgets. Okay. So what I've done is I've taken these lines and I've used a widget called measure the length of a curve, right? And that gives me the length of each of those lines that I've drawn. So now I can start to determine the length of span for each truss, right? Then I can just use a simple division widget from the maths tab, right? And I can take each of those and divide it, you know, by some sort of denominator. In this case, I picked 18. Typically, you know, there's some rules of thumb out there, and they really differ. But just, you know, for example, if I was going to do what I learned growing up in architecture school, right? You know, sort of quick rules of thumb before you do the actual structures, right? You could take, let's say, the span, and for every foot, you have to sort of have a depth of 1 inch. So let's say I was spanning 25 feet. I would start with 25 inches of depth and add 6 to it. So then I would be in sort of in the neighborhood of 31, 32 inches of depth for my structure, right? And that's sort of a rule of thumb. It's like going to the studio companion and sort of saying, well, let's say my floor to ceiling would be, you know, X, Y, Z. You know, you could then, you know, have I think a really intelligent conversation with a structural engineer. She or he might tell you then, you know, well, okay, here's the W shapes that you'd be using, and here are the depths, and then you could fine tune things very precisely after that. But just to sort of as a rule of thumb here, right? So, and so that's what I've done, right? And so in this graph, right, the depths of each of these trusses is directly proportional to how far they span, right? So this depth, the depth of this truss over here is much less than the depth of the trusses over here because the span is different, right? The span is shorter, right? So the distance between the walls and that span distance that this truss has to cover is smaller, and therefore it doesn't have to be as deep, right? And those things start to step up as you move across the volume here, right? So if you begin to immerse yourself inside, you can start to see it's starting to become quite a dynamic space here. All right. And then the last sort of part of this is we'll start to build in more and more of these relationships. But I'll show you, in this case, I think I was just doing this before. I've named this file bow trusses 03, bow trusses on steroids. All right, and so in this case, what I've done, instead of having these sort of bearing walls, is I've also made a set of wall structure with these sort of vertical bow trusses. And so now this is like trusses on trusses on trusses. So the walls are this sort of structural truss system. And then we have these structural trusses spanning between them. Of course, the problem here would be this sort of pin connection at the corners, unless the actual overall geometry created some sort of shell-like shearing, geometry. This would be the problem, right? So we'd probably beef up these corners quite a bit with bracing here, but if we were really talking about structures. But I just wanted to sort of show you guys this. Right now, we can begin to think about this sort of this immersive generative lattice, right? That begins to define spatial volumes that we can actually place ourselves inside, and then use later on as a sort of piece of architecture, then build a collage, a sort of experiential perspective collage of, right, in Photoshop, right? So this is eventually the sorts of things that we're going to talk about, is how do we go from this sort of technical side of Grasshopper to really making things that are spatial, volumetric, and then how can we build up this sort of design, visualizations and perspective. Also thinking about maybe an exploded axon, line drawing, and some of those other sorts of sort of representation and drawings that you can go back and forth in between our CAD softwares like Rhino, Grasshopper, Revit, AutoCAD, and then the graphic software like Photoshop and Illustrator. Right? So, okay, so I'll start from scratch. Let me just close these out. All right, and again, a lot of this will be review of stuff you've done, but what we'll do is we'll start to build some relationships, some smarter relationships between some of this geometry that we make based off of some of those bow truss recipe that we started with. Okay, so first and foremost, I have this curve and I have this curve. I've built them in Rhino. I'm going to use these in Grasshopper, right? And so I first need some of these curve placeholder widgets. I'm just going to go ahead and pull those in. Make a copy of this one. I'm just going to right click on this first one. I'm going to say set one curve. Grasshopper will disappear, basically telling Grasshopper, hey, I have some geometry in Rhino. I need to bring it in, reference it into Grasshopper, and start to use it in my parametric graph here. Okay, so now it turns from orange to gray, meaning that there's some data being fed into this, right? Right click on this one, say set one curve, and do the exact same thing. I'll pick this curve over here. All right. Okay. And now first things first, what I'm going to do is I'm going to take each of these curves. Let's just talk about that recipe again, just as a reminder. I'm going to divide them a certain number of times, right, in order to get a set of points that moves across those. And with those points, I'm going to use them as start and end points in order to draw lines across, right? And then that's the sort of starting point for our bow truss from before, right? A sort of line that determines that sort of direction, orientation, length, and span of our trusses, right? From there, we'll place a point along each of these, right? We'll go up, I'll go down, I'll draw a sort of arc here and an arc here, right? Or a spline, right? Interpolated curve. I'll divide each of these curves up and start to create the webbing in between. All right, so that's the that's the sort of idea here. That's the workflow. You know, that's the sort of way we're making trusses for this particular recipe. All right. Okay. So I have curves. I needed to modify those curves. I needed to generate them in this case, or generate geometry from them in this case. I'm going to divide them. So I'm going to go to my curve widget, or my curve tab, sorry, and look at this, all these sort of different tools and widgets I can use for curves. This one called division seems to be pretty apt. So I'm going to divide each of these curves. Right. So I'll plug this in. By default, the number of divisions will be set to 10. I'm going to make this parameter of the number of segments a variable. So I'm going to go to the params tab. In this case, I'll use a number slider. That way I can change that slider. I can move that tick mark back and forth along a number line and change this value. I'm going to double click on that number slider. Okay. I'm going to constrain this to integers. I don't want to really like have like 13 and a half segments. I either want 13 segments or 14 segments. So I constrain this to integers. I never want to divide things by 0. That's just a no-no in math. So I'll change the minimum to 1 and the maximum to some larger number. In this case, I'll pick something really large, ridiculously large, like 500. Okay, hit enter. Once I like all of these sort of settings and parameters inside of my number slider, I'm going to hit OK. Go ahead and stick that in. One division will give me a point at the beginning and a point at the end, right? And one segment in between, right? If I move that, right? Sorry, I was just trying to move it once. So 2 segments, right? Divide the curve into 2 segments, right? I get 1, 2, 3 points, right? So one at the start, one at the end, and then one in between at that division point. Okay, and so the number of divisions and the number of points we get out will always have a difference of 1, right? So 36 divisions gives me 37 points, right? Okay. Something that sometimes just never makes sense until you look at it and go, oh, okay. All right. Once I have this set, I'm just going to do the exact same thing. I'm just going to copy and paste this, Control-C, Control-V. And I'm just going to plug this curve in, the same widget, the same number slider here, right? And I'll get a list of points, 37 of them, 37 of them, okay? These are my start points and end points. I'm going to make a line that spans between each of these start points and end points, right? So I'll plug these set of points in for A, these set of points in for B, right, for this line widget. Okay. It's one way to make a line. I need a start point and end point. I'm just going to draw the shortest distance in between. That's always going to give me a line, at least in typical Cartesian coordinate space, right? Okay. All right. Now I'm just going to get rid of these start and end points now. Yeah. I'm just going to right click and turn the preview off. Now let's clean up this preview for me so I can see things a little easier here. Okay. I'm going to blow up my perspective view and move it over to the left-hand side. I'm going to move my Grasshopper window over to the right-hand side. And that way these two things can hopefully coexist on my screen and you guys can see both at once here. All right, so I'm going to take each of these lines and I'm going to analyze them. I'm going to evaluate them at a t parameter, right? Okay, so in other words, I want to find a point or a moment along each of these lines. And so I can do that by sort of thinking about where that t parameter will exist. So I'm going to plug in these lines, this tool, evaluate curve at a t parameter. I'm going to right click here where I plug in the curves. I'm going to toggle on this reparameterize, right? What that does is instead of each curve having a different length, right? What I want to do is I want to normalize the t addresses between 0 and 1. And that way I can find endpoints and midpoints, comparable points along each of these curves parametrically. And so now I can use this number slider and plug that in for a t parameter. There we go. And now I can go from the endpoint at 1, the start point at 0, or any sort of moment or location in between. Just in case, I'll just type in 0.5 to be precise there. You can go to 3 decimal places. You can go to more if you double click, right? You can always give it more decimal places here. I don't know why you'd want to at a certain point, right? The tolerances here for architecture are not usually that that exact, but to thousandths and millionths of an inch or anything. So, all right. So let's see. Now we have these points, and here's a funny thing. I'm just going to, again, just like we did with our bow trusses, right? I'm going to go to our curves tab, look at my primitives, right? Just like I can make a line with a start point and end point, I can also make a line with a start point, direction, and length. And these will be my start point. For my direction, I'm going to go to vector. I'm going to use my Z axis. There we are, my direction. And then for length, I'm just going to feed in, right? I'm going to make that a variable again. So I can change that value depending on what my engineer tells me, right? So let's say my engineer says, oh, these things have to be 3 feet deep, right? I can change that number here in my number slider and adjust them accordingly, right? So let me just adjust the minimum maximum here. Let's say I'm working in feet, so right, I can start to go anywhere between 0 feet and 5 feet or something like that. Okay, and I'm just going to make a copy of this because I wanted to make a sort of a bow-shaped bottom chord as well, instead of having a straight bottom chord. Right. So in this case, I'm still going to use the Z direction, but in this case, I just want to change the length from the positive to the negative. Right. I actually wrote a custom expression here, but another way to think about this is I can just take this number, right? It's going to be the exact same number, and I'm just going to multiply it. I'm going to find the maths tab. I'm going to go to the operators and just use a multiplication widget. I can multiply one number against another number. So here I'm going to multiply whatever this number slider value is, right? Plug this in, and I'm going to multiply it by -1. So I'll just type in -1 here. All right, so that's going to give me the exact same line, but in the opposite direction, right? So as these things grow in height, they'll grow in depth in both directions, height, up and down. Oh yeah, look at that. Hopefully you guys can see that here. See those green lines sort of growing up and down from that center point. Okay. All right. So now I'm just going to, again, similar to your recipe before, I'm going to find the endpoints for these. Okay. So I'm going to find a curve start point and endpoint. I'm going to really just use these endpoints. All right. And so let's just take a look. I'm just going to try the recipe, right, as we did before. And go to the spline, interpolate curve. I'm going to hold down the shift key, and I'm just going to try this. You'll see what the problem is going to be here in a minute. I'm going to take these set of vertices, these points as vertices, and these points as vertices. And what it's going to do is it's going to draw a curve through all of these, and then through all of these, and through all of these, just one curve. It's going to take all of these lists and string them together as one big list and just draw one big curve that sort of spans in between them and goes all the way through. And that's going to be really odd, right? What we want is for them to sort of pick just this point and this, and each of these points, right? And then each of these points, and then each of these points. And so that's why I've used a data tree to do that. Again, I don't expect you to understand why that works, but suffice to say, for now, it's enough if I just sort of graphed each of these into a data tree before I plug them in. Do this and this. Okay. And I'll do this over here, but in this case, I'll use these endpoints. All right. Okay, now I'm going to do this. So let me find my splines, interpolated curves, hold down the shift key, plug in multiple inputs at the same time. For whatever reason, this one doesn't look, oh, it's because I plugged in the wrong thing. There we go, that would help. Yikes. All right, so this gives me my top chord. I'll do the same thing over here. This gives me my bottom chord. I'll hold down the shift key, my keyboard. All right. Again, we're getting something very similar, but this time instead of making one bow truss, we're making a bunch, right? All at the same time. Okay. Now, I'm going to selectively clean some things up here. But one thing I'm going to do before I start to get to all the webbing is let's go ahead and look at that relational, the sort of depth as it relates to the length of each span, length of span of each truss. Okay, so I'm going to go start to get rid of some of these points just because they really sort of they really make it difficult to sort of see some of these things. But so let me just turn some of these things off. I'll select all of these at once and turn the preview off. There we are. Now, hopefully we can just see the span line and then these curves themselves. All right. And so what I'm going to do is these lines, these green lines, right? These original lines that sort of just talk about the span. I'm going to go to the curves tab and under analysis, I can also find the length of each curve, right? So I'm going to do that. I can find a length of a curve. If I plug in this list of curves, right, I'll get a list of lengths, right? So each curve has a length, and I'll get the list of all of these lengths that I can use, right? And then it's a matter of just sort of setting up some sort of ratio, right, between the length of span and the structural depth needed, right? So I can do this any number of ways. I can do division and divide by a whole number. I could do multiplication and divide by a fraction or a decimal value. So maybe I'll do that, right? Maybe I'll say that if you take the length, the depth is 0.2 or 0.15 of each length, right? So in this case, I'll actually make this a parameter that I can use, right? Or a sort of variable I can adjust, right? I'm going to plug these in, right? And so now I'm going to make a list of custom depths, right, for each of these heights, each of these distances. I'm going to plug this in, right? Oops, I plugged it into the direction instead of the length. So let me just accidentally do this. There we go. Right. And I'm going to adjust that down because I'm also doubling it because we're going in the top and bottom, right? And so now you can see, right, that each of these depths are now different, right? And so, this is the thing, right? Each of these trusses have a different situation, a different span. And so they each have to perform a little different than its neighbor, right? And so they're going to be different when it comes to their sort of structural depth. All right. And so that's one way to begin to sort of build in a sort of smarter sort of way of thinking about this, right? A lot of these things are proportionally related to each other, right? Maybe it has to do with structure, maybe it has to do with aesthetics, maybe it has to do with the sort of typical size that, let's say, a bar stock steel comes in, or a piece of plywood comes in, or that glass windows come in, or whatever, right? But there's oftentimes the sort of relationships between these things, and that's another thing that we can start to build in here in order to make these much smarter. Okay. All right, great. So now we can take this, and I'm going to start to build in the webbing, the sort of cross webbing. I'm going to turn off this preview. All right, there we go. I'm just going to use these as chords, right? Top and bottom chords. Now I need to divide them up. All right, so curve, division, and divide curve. Just going to do this for the first one. I'm going to make this number slider that's going to be really nice and easy. I'm going to double click on the number slider. Again, make this a variable, constrain it to integers, set that minimum to 1, maximum to something larger than like 2, 20, 20. There we go. 20 divisions, something like that. Right now I can start to change, right, how much webbing I have. Right. Okay, great. Now I can copy and paste this widget, plug in the bottom chords as well. All right, so now they'll each have the same number of divisions because I'm using this slider for the divisions for the top chord and the divisions for the bottom chord, right? I want to make sure that those things stay the same. All right, now I have a set of points and I can connect them up one to one in order to create these sort of vertical webbing, right? So here I'll make a line widget, start point and end point, right? Yeah, excellent. There's a lot of points here to connect up, right? And so it's nice that it's remembering both the sequence of these things and which points belong to which curves for us, all because of these data trees, right? Again, you'll get to that, why that works later on in the semester when we start to really look under the hood here. But suffice to say, for now, it's just kind of nice shortcut that actually works for us. I'm going to take each of these lists. I'm going to shift them just like we did before. Go to sets, shift the list over by one value for each of these. Copy and paste that. Shift this list over. There we are. All right. And I'm going to start making some more line widgets here. There's one. Before I start to connect those up, make another one. All right, now I'm going to connect these set of points with the shifted list of points, and then these shifted list of points with these list of points, unshifted list, right? And we start to get these diagonals moving through. All right. This wrap value needs to be set to false, right? I saw a couple of you miss that step with your truss values. There we are. All right. Now we have, right, we can begin to determine, based off of our roof system, right, the spacing in between trusses and how many we have and their density, right? Their structural depth, right, based off of their span, and the amount of webbing that we need, less or more, right? Okay. And then again, right, let's tube these, let's pipe these. Why not? I'll go to surface, and I'll go, in this case, I'll just pipe them with a radial pipe, right? So a circular pipe. So for the input here, we have a base curve, right, or set of curves to pipe along, right? We have the radius, right, for the sort of cross-sectional circle that's swept along each of these paths. And then we have the end caps. I'm just going to select none, and for the time being, if I was really careful, I'd probably pick that, but I'm not going to worry about that too much. All right, now let's look at this. I'm just going to pipe, just going to plug this in, and this in, and these in, right? And now I'm just going to go to the radius. I'm going to, oh, you know what I'm going to do? I'm going to make that a variable. All right, there we go. I'll make that much smaller. Yeah, there we go. All right. Okay. Now, let's do this one more time, but I'm going to go to my pipe command. I'm just going to do this maybe a little differently this time. All right, I'm going to use this radius here, and I'm going to plug in my top and bottom chords. Right, so in this case, there we are. I'm going to plug in this one. I'll plug in this one. All right, so let's say that there's a sort of radius that we're going to use for the top and bottom chords. For the webbing, there's a hierarchy here. The top and bottom chords need to be a little beefier than this sort of cross webbing, right? And so the webbing is going to be a ratio, a proportion, a fraction of the radius that we're using for the chord, right? So in this case, I'm going to disconnect this. And again, I'm going to go to my math tab. By default, it's gone to something silly like 1. That's way too thick, of course. But I'm just going to go to the math tab. I'm just going to say, let's take this radius that we're using for the top and bottom chord, and let's multiply it by, again, a variable. In this case, I'll set it to like 0.6. It'll be about 60%. Let's see, 0.6. There we go. And we'll use that as the radius for the webbing. So the webbing will actually be smaller than the radius of the, the sort of the cross-sectional depth of each top and bottom chord here, right? All right, again, sort of building these geometric relationships between these things. All right. And again, I'm not expecting you to follow along here. We're just taking this and drawing out to its most logical conclusion as a demonstration. But again, you can always go back through and sort of say, well, there would be a relationship here. You can always sketch these things out on paper, right? And sort of say, structurally, right? This span, right? And then this depth, there's a relationship there, right? And geometrically, we can actually build that in. especially if this span changes, right? Then it makes no sense to give a constant number for this depth. But what we can do is we can make this depth a ratio of each individual unique span, right? And so, and again, we can take that through. In this case, we're talking about structures. So, the thickness of the materials and the cross-sectional geometry of each component, right, then begins to vary, right? So we can make the thickness and radius of these change as well based off the span, right? And begin to build this sort of rich set of relationships. And that in itself is a sort of complex model, right? Complexity meaning interdependence, right? The fact that we have a number of relationships, right? And interdependencies between, or dependencies between a number of pieces of geometry. And as we start to make adjustments to something upstream, everything downstream begins to adjust the way we need it to, because we've thought through all the rules, right? We've thought through all the relationships and associations that are required in order to make this thing really sort of performative in a particular way, right? Okay, so I'll just clear that out. All righty. So the last thing I'll do here, and again, there's a way to do this with data trees without having to sort of copy and paste, but let's just talk about this because this is something that you'll do here, right? I'm going to copy and paste everything, a copy of all of this graph, except for my count, my original count here. My original count, I'm going to leave, everything's going to be governed by this original count here, including these copies that I make. I'm just going to copy, and I'm going to paste. I'm just going to make another one down here, right? But instead of spanning between, oops, sorry about that. I'm just going to delete this wall away. But instead of spanning between this top edge and this top edge, I'm going to span between this top edge and this bottom edge of this one wall and actually create a set of vertical trusses that structurally would hold up, let's say, a curtain wall on the outside. Okay. And then also would translate the loads of these trusses, from a lateral set of forces down to a vertical set of forces to the ground. All right, so let's try that. First things first, I'm going to change the ingredients, right? Theoretically, most of this should work if I just change the two curves that I'm spanning between. So instead of spanning between this top edge and this top edge, I'm going to span between this top edge and this bottom edge. So I'm going to right-click on this widget, right, and say set one curve. I'll make sure I select that curve. Then I'm going to right-click on this one and set one curve. I'm going to select this one. All right, now let's see what happens here. All right, everything looks good, except nothing is structurally thick, and that's because we made an assumption right here that we would make the thickness, or the structural depth of our trusses in the z-axis, which makes sense if we're spanning laterally. Doesn't make sense if we're spanning vertically, right? So in this case, what I'm going to do is I'm going to find the perpendicular to this curve for each of these points, right? Okay, so in order to do that, I'm going to take this bottom curve, and instead of just dividing it, I'm going to go to the curve tool. So I'm just going to go to division. And instead of just dividing the curve, I'm also going to say, populate this with a set of perpendicular planes or frames, right? So I'm going to take this, I'm going to divide it the same number of times as I did before, but now I'm going to populate it, each of those divisions, with a set of perpendicular frames. And then I'm going to take the x-axis for each of these planes, and I'm going to use that for my direction instead of the z-axis for my direction. All right, so now we're taking each of these, again, as I move across this curve, right, those directions are going to change. Yeah, it's going to be really flipping sweet. All right, so anyway, let me do that. I'm going to take each of these planes that I've created now, and I'm going to deconstruct them in order just to find each one's x-axis. I'm going to take that x-axis, and I'm going to plug that in for the z here and here. Oh, yeah. Look at that. All right, now if I go into top view, you'll see that these will quite literally match up as a sort of perpendicular for each of these, right? So the perpendicular at each of these points along this sort of curve that changes, right? So if you're thinking about calculus and how how the slope of a curve changes as you move across it from one start or one from the beginning to the end. Not only is that tangent change the slope, right, but also the perpendicular to that slope or tangent, right, the normal, right? And so that's what we're doing, is we're using the normal of the curve at each of these individual moments or points along it, right? And then we're using that as a direction, right? We can do that with the other one as well, right? So now that I have that, I'm just going to zoom out. I'm going to take this new recipe that we made for the side. I'm going to copy. I'm going to paste that. I'm going to move this down, right? And now I'm just going to change those ingredients once more. So let's get rid of this wall. Yeah. All right. And I'm going to set one curve. I'll select this top curve. Right click, set one curve. And I'll change this, or select this bottom one. Now we have more trusses than we ever cared to have, right? And if I, again, go to perspective, and let's put myself somewhere inside here at eye level. Like, oh, that didn't work out so well. Here, let me try to act a little smarter for the rest of the class time here. Sort of, again, immerse myself inside. All right, tilt this down so that it looks like I'm, a 6-foot person inside a, let's say, a 25-foot space. Right? Holy moly, that's a lot of trusses, right? And again, the information flows from left to right. And so, again, as I change this count, let's say to 75, right? Everything downstream changes with it. Now, it might take a while for it to all calculate, right? Because remember, it's got to divide each of those curves up into points, connect them all with lines, divide all of those, then use those and create top and bottom chords, then divide those up and start to draw all the zigzags, and then pipe everything into surfaces, right? And so, again, but all of that stuff changes over time, right? And so we could begin to, again, make all of these associations between things and begin to generate something, quite interesting here. So at the end of this, I can save this Grasshopper file. Now, once I have something that I want to use and to sort of bring back into Rhino, right? What you'll notice is that as soon as I close Grasshopper, it all disappears, right? And as soon as I open up Grasshopper and I make sure that I've set these ingredients up again, it all reappears, right? Once I'm done, I can start to select these widgets that I want to bring back into Rhino, right? So all of these pipes that I've created. Okay. If I right click on them, you can see there's an option called bake, right? So I can bake all of these back into Rhino, right? I have more than one widget. And so now that I have all of these selected, you can see them turning green. Here in solution, I can bake them all at once. I can say baked selected. So all the things that are turned green that I've selected, I can bake them back into Rhino. It's going to take a minute. You can see my cursor turning blue. Now I can close this up. Right now I have a static version of it with whatever parameters I was using right here in Rhino. At this point, maybe I turn things to rendered. Let's see what this looks like. Right, I can start to get some soft shadows. If I go into the rendering settings, not only can I turn on just the skylight, but I could also turn on the sun. Let's see what this looks like with some crisper shadows. Let's see. Right. I can always change the time of day and my latitude, longitude. So in this case, I could turn my sun settings on. Let's see what it has by default if I sometime today. Oy. Okay. Not sure why this is taking so long. It really shouldn't. Right, but I can begin again to sort of think about this sort of spatial architecture that I've started to enclose. Right. Sometime today. It says not responding to the sun settings. I don't know why. It doesn't seem like that would be too difficult here. Right, so in this case, it picked Accra, Ghana. I'm not sure why, but I could always tell it I'm in Las Vegas, Nevada, of course, not Dallas, Texas. I don't know why about that here, right? So that's going to set my latitude where I need it. And therefore, it's going to start to determine my solar geometry. And so I can give it a day and time of the year. Let's say, in this case, maybe I'll pick September. Maybe. Let's pick the 21st. I'll pick an equinox. And this is at solar noon. Let's actually pick, let's say, 3 p.m. or so. Maybe. Right. And let's see. Okay. One other thing I can do is I can change its intensity. Not sure why. There's an intensity of 1. See what happens when I do that. Theoretically, it should draw sort of crisper shadows cast by the direct sunlight as well as the soft shadows by the diffuse light, right? So I don't know if you guys have studied this yet, but you know, everything that we see, of course, is because light's bouncing off of it back to our eyes. That light sometimes includes direct light directly from the sun, but a lot of the light that we see is also sort of scattered throughout the sky vault by dust and moisture. And then everything that we see, of course, has been bounced off of an object back to our eyes. So, you know, depending on the road conditions and surfaces and how bright things are and the building facades and you know, all this sort of things, right? We get a bunch of light bouncing around. And so we get both crisp shadows and soft shadows. I'm just going to turn the sun off though. Seems like that's really bogging down my system here. Just turn that off. Just get some nice soft shadows, right? Sort of a white clay model rendering. Haven't added any materials or shaders yet. Haven't really done much except to sort of understand some tonal values and start to understand depth and distance, right? All right. If you're interested in taking some of your screenshots this way with render mode on, right? When I right click on my viewport settings, instead of doing shaded or ghosted X-ray, you can do that and you can go to view, capture to file. And then it'll sort of say, do you want to capture this viewport? And if so, you know, what scale, how many pixels in the sort of width and direction, and hit OK. And then you can save a JPEG or a PNG, depending on if you want the transparent background or not, right? Some of you, I think, have figured that out. And maybe I showed that to you in the videos. Other times, you're just probably taking a print screen from your operating system, right? Either way, at this point, I'm not so keen either way. It's just sort of making sure that you're able to follow along and getting things to work, and hopefully that things are making sense conceptually with sort of how these things are being built, the actual recipe itself, right? So at any rate, at this point, I'm going to stop sharing. I'm going to stop recording.